Tonight we are going to look at the moon nobody talks about. Not Io, with its hundreds of active volcanoes and rivers of molten rock. Not Europa, with its hidden ocean and its place in every conversation about life beyond Earth. Not Ganymede, the largest moon in the solar system, larger than the planet Mercury. Callisto, the other Galilean moon. The quiet one. The heavily cratered, geologically dead, scientifically overlooked fourth member of Jupiter's inner family. The one that tends to get a paragraph in textbooks while the other three get chapters. And here is the thing that should unsettle you. Of the four great moons of Jupiter, Callisto is the only one where humans could actually survive on the surface. Not in a sealed radiation bunker buried under rock. Not in a specially designed shelter with meters of lead shielding. On the surface, with manageable radiation exposure. With water ice within reach. With a geologically stable foundation beneath them. With a clear view of Jupiter hanging in the black sky overhead. Every other moon in the Jovian system would kill you quickly and without apology. Callisto is the exception, and the more you understand what that means, the more disturbing it becomes that we have barely studied it. By the end of tonight, you are going to understand what Callisto actually is. Why the thing everyone ignores about it is in fact its most important feature. What the oldest surface in the solar system tells us about the history of everything. And why the quietest moon in Jupiter's family may be the most consequential destination in the outer solar system. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Jupiter has four large moons, known as the Galilean moons, because Galileo Galilei discovered them in January 1610 with one of the first telescopes ever pointed at the sky. This is one of those facts that is so familiar it can slide past without leaving a mark. Galileo, looking at Jupiter through a crude early telescope in the middle of winter, noticed 4 points of light that moved from night to night in a pattern that made sense only if they were orbiting the planet. Over the course of a week, he tracked their positions carefully enough to establish that they were separate objects following separate orbits. He had discovered a system of worlds orbiting a planet that was not Earth. The implications were enormous, and not just scientifically. Galileo's discovery provided direct, observable evidence that not everything in the sky moved around Earth. Some things moved around Jupiter. The idea that Earth was not the centre of all celestial motion, which was already being argued from theoretical grounds by figures like Copernicus and Kepler, now had an unmistakable visual demonstration that anyone with a telescope could verify. 4 moons orbiting Jupiter were something you could see with your own eyes. You did not have to take anyone's word for it. The 4 moons discovered in January 1610 are still orbiting Jupiter. They have not changed significantly in the 4 centuries since Galileo first noted their positions. Callisto is still out there, at the same distance, in the same orbital position relative to Jupiter's radiation belt, holding the same ancient surface, with the same water ice and the same craters and the same quiet that has characterized it for 4 billion years. In the 4 centuries since that discovery, Io, Europa, and Ganymede have become some of the most discussed and most anticipated destinations in the solar system. Io is the most volcanically active world known to exist. Its surface is constantly being reshaped by hundreds of active volcanoes, driven by tidal heating from Jupiter's immense gravitational pull. The same gravitational force that keeps Io in its orbit squeezes the moon's interior continuously, generating heat, melting rock, and sending plumes of sulfur hundreds of kilometers into the sky, Io is violent and dramatic and photogenic and endlessly surprising. Every time a spacecraft has looked at it, Io has done something new. Europa is the darling of astrobiologists. Beneath its cracked and refrozen icy surface lies a liquid ocean that may contain more water than all of Earth's oceans combined. The same tidal heating that drives Io's volcanism keeps Europa's subsurface water liquid. And where there is liquid water in contact with a rocky seafloor, Earth's own ocean floors have shown that life can appear without sunlight, without warmth from above, powered entirely by chemistry. Europa's ocean is one of the places in the solar system that scientists most urgently want to examine. Ganymede is the solar system's largest moon, wider than the planet Mercury, with its own internally generated magnetic field, an intrinsic feature no other moon anywhere is known to possess. It also has a subsurface ocean, and its layered structure hints at a complex geological history. These three moons collectively account for most of the scientific attention, most of the mission proposals, and most of the headlines about Jupiter's system. And then there is Callisto. Callisto is the outermost of the four Galilean moons. It orbits Jupiter at a distance of roughly 1.88 million kilometers, which is about 5 times farther from Jupiter than our moon is from Earth. A full orbit takes about 17 Earth days. Its diameter is 4,821 kilometers, making it slightly smaller than Mercury and significantly larger than Earth's moon. It is the third largest moon in the solar system. In terms of raw size, Callisto belongs in the conversation with the giants. But when you look at Callisto's surface, the first reaction is not awe. It is something closer to weariness. Every square kilometre of Callisto's surface is covered in impact craters, old craters overlapping older craters, with even older craters beneath those. The surface is so densely cratered, so completely saturated with the record of ancient collisions, that planetary scientists have a specific term for this condition: saturation cratering. New craters cannot form without destroying old ones, because there is no available surface left between the existing craters. Callisto holds the record. Of all the surfaces in the solar system that have been imaged in sufficient resolution, Callisto's is the most heavily cratered. It carries more impact scars per square kilometre than anywhere else in the known solar system. This makes Callisto look, at first glance, like the geological museum piece of the Galilean moons. A dead world that has been sitting there accumulating hits for billions of years. Nothing happening inside. Nothing dramatic on the surface. Just craters on craters on craters, stretching in every direction. And that first glance is deeply misleading. To understand why Callisto looks the way it does, you need to understand why the other Galilean moons do not. Io, Europa, and Ganymede are in a gravitational relationship with each other, called an orbital resonance. For every orbit that Ganymede completes around Jupiter, Europa completes exactly 2, and Io completes exactly 4. This is not a coincidence. It is a locked, self-reinforcing gravitational pattern that emerged over billions of years and now keeps the 3 inner moons in a perpetual gravitational tug-of-war with each other and with Jupiter. The consequence of this resonance is tidal heating. As Io orbits Jupiter, the gravitational pull of the planet and the gravitational pull of the neighbouring moons continually deform Io's interior, squeezing and flexing it like a rubber ball being squeezed by strong hands. The friction from this constant deformation generates heat. On Io, the heat generated by tidal flexing is so enormous that it melts rock. On Europa, tidal heating keeps the subsurface ocean liquid. On Ganymede, the effect is less extreme but still significant. Callisto is not in this resonance. It sits outside it. At its greater orbital distance, the gravitational coupling that drives tidal heating in the inner three moons does not apply to Callisto in any meaningful way. The result is that Callisto has never been significantly tidally heated. Its interior never generated enough heat for rapid differentiation, the process by which heavier materials sink toward the core and lighter materials float upward. Io, Europa and Ganymede are differentiated worlds, with distinct layers, rocky mantles, icy shells, liquid regions, metallic cores in some cases. Callisto is internally a relatively uniform mixture of rock and ice in roughly equal proportions by mass that never fully separated. Callisto never had the internal heat to drive volcanism. It never had the forces to produce plate tectonics, or any equivalent. Its surface has not been reshaped from within for billions of years, and so the craters have accumulated, undisturbed, since the early solar system. What looks like a dead world is actually a record, the most complete, most undisturbed record of the impact history of the outer solar system anywhere in existence. There is a feature on Callisto that most people have never heard of, and it is one of the largest impact structures in the solar system. It is called Valhalla. Valhalla is a multi-ring impact basin, the scar left by an enormous collision that occurred billions of years ago. At its centre is a bright, smooth region roughly 600 kilometers across. Surrounding that centre, extending outward in concentric rings of ridges and troughs. The structure reaches a diameter of about 3,800 kilometers. To put that in scale, 3,800 kilometers is roughly the distance from London to Riyadh. The central smooth region alone is wider than France. This is a single impact scar, one event, preserved in the surface of Callisto. When an object large enough to create Valhalla struck Callisto billions of years ago, the impact was so energetic that the shockwave propagated outward through the icy crust, deforming it in concentric rings like ripples in a pond that froze in place. The central region was briefly liquefied and then refroze as a smooth plain. The rings preserved the geometry of that moment, locked into solid ice and rock, and have been sitting there ever since. Valhalla is not the only large impact basin on Callisto. Asgard, another multi-ring structure, reaches about 6,700 kilometers across. Dozens of named craters cross Callisto's surface. The Moon is effectively a planetary record of what was hitting the outer solar system in its early history, preserved in a format that could not be more legible to scientists who know how to read it. This is the first reason why Callisto, which appears boring, is anything but. Now we arrive at the feature of Callisto that should have elevated it to the top of the priority list for human spaceflight planners decades ago. Jupiter has the strongest magnetic field of any planet in the solar system, roughly 20,000 times stronger than Earth's magnetic field. This magnetic field is not gentle. It accelerates charged particles, protons and electrons, to extremely high energies and traps them in radiation belts surrounding the planet. These belts extend outward from Jupiter and intersect with the orbits of the inner Galilean moons. The radiation at Io's surface is lethal beyond any reasonable description. Unshielded exposure on Io's surface would deliver roughly 36 sieverts per day. A sievert is the unit measuring radiation's effect on biological tissue. Exposure to 5 sieverts over a few days is fatal. A full day on Io's surface without any shielding would deliver radiation roughly 7 times the lethal dose. Europa is only somewhat better. Its radiation environment delivers roughly 5 sieverts per day to anyone standing on its surface without shielding. That is still enough to kill an unprotected person within days. The ice beneath Europa's surface would need to be penetrated to reach the ocean below, and any long-term surface operations would require extraordinary shielding against the continuous bombardment. Ganymede has a magnetic field of its own, which provides some local shielding from Jupiter's radiation. Surface radiation on Ganymede is lower than on Europa, around 0.08 sieverts per day, which is still high by any standard, but not instantly lethal. Long-term habitation on Ganymede would require significant radiation protection, but is not as immediately catastrophic as Io or Europa. And then there is Callisto. Callisto orbits outside the main boundary of Jupiter's radiation belts. Jupiter's magnetosphere does reach Callisto, but the intensity of the charged particle flux at that distance is radically lower than at the inner moons. The radiation dose on Callisto's surface is approximately 0.01 rems per day. To understand what that number means in human terms, Earth's average background radiation is about 0.0024 sieverts per year, or roughly 0.00066 rems per day. Callisto's surface receives about 15 times more radiation than Earth's average. That is elevated. It is not harmless. But it is also lower than the radiation dose you receive during a single transatlantic flight at altitude, lower than living at high elevation, and substantially lower than what astronauts routinely experience on the International Space Station. On Io, lethal in hours. On Europa, lethal in days. On Ganymede, dangerous without shielding, survivable with it. On Callisto, elevated above Earth, manageable with minimal protection. One moon in Jupiter's inner family allows human surface operations without requiring extraordinary radiation infrastructure. One moon sits outside the kill zone, and it is the one nobody talks about. The resources available on Callisto's surface make the radiation picture even more significant. Callisto is composed of roughly equal parts rocky material and water ice, with the ice component constituting somewhere between 40 and 55% of the Moon's total mass. On Callisto's surface, this water ice is directly accessible. It is not buried kilometers deep beneath a shell of rock. It is part of the surface itself, mixed with the rocky material in what planetary scientists describe as a dirty ice composition. Water is the most important resource for any space settlement. It provides drinking water. It can be electrolyzed into hydrogen and oxygen, providing breathable air and rocket propellant. It provides radiation shielding when placed around habitats. It is the raw material for countless chemical processes. In the outer solar system, water ice is abundant, but access varies enormously depending on location. On Callisto, it is on the surface, in a radiation environment manageable enough that robotic mining operations could function without constant shielding overhaul. The accessibility is not incidental. It is a core part of what makes Callisto uniquely attractive for a future human presence. In addition to water ice, spectrographic analysis of Callisto's surface has detected carbon dioxide, sulfur dioxide, and various organic compounds. These materials have their own uses in any settlement or industrial operation. Carbon dioxide can be a feedstock for chemistry. Organic compounds can be precursors for more complex synthesis. The silicate and rock component of the surface provides raw material for construction. Callisto's resource profile is not as exotic as Europa's buried ocean or Io's geothermal energy, but it is more accessible, more directly usable, and obtainable under conditions that would not immediately threaten the lives of the people doing the obtaining. The question of whether Callisto has a liquid ocean of its own is one of the more genuinely uncertain scientific questions in the Jovian system. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, provided the most detailed study of all 4 Galilean moons yet conducted. When it flew past Callisto, it detected an unexpectedly strong ionosphere, an electrically charged layer of the thin atmosphere. The most straightforward explanation for the ionosphere's intensity is the presence of molecular oxygen in greater quantities than the surface alone could readily produce. And the most straightforward explanation for the molecular oxygen is the existence of liquid water beneath the surface, where chemical processes could generate oxygen and allow it to escape upward into the tenuous atmosphere. The Galileo magnetometer data also showed perturbations in the local magnetic field when the spacecraft flew past Callisto. The pattern of these perturbations was consistent with the presence of a conducting layer beneath the surface, as would be produced by a saltwater ocean. But the signal was weaker than those detected at Europa and Ganymede, and Callisto's greater distance from Jupiter means the tidal heating that maintains the inner moon's oceans is largely absent. If Callisto does have a liquid ocean, it is likely maintained by a combination of residual internal heat, the decay of radioactive elements in the rocky component, and possibly some geothermal activity too subtle to have produced surface features. The ocean, if it exists, is probably deeper beneath the surface than Europa's, colder, and less in contact with rocky material that could provide the chemical energy sources that make Europa's ocean so promising for life. The scientific community is genuinely uncertain. Some models suggest a deep liquid layer is plausible, others suggest it may not exist at all, and the ionosphere observations may have a different explanation. Resolving this uncertainty is one of the scientific goals of upcoming missions. In 2003, NASA conducted a planning study with the long name Revolutionary Concepts for Human Outer Planet Expansion into the Jovian system. The acronym was HOPE. The study asked a specific question: if humanity were to establish a human presence in the outer solar system, where should we go? What location in the region beyond Mars would be most practical as a base of operations, a staging point for further research, a place where humans could work and survive for extended periods? The answer the study reached was Callisto. Not Mars, which was already well studied, not the asteroid belt, not Europa despite its scientific importance, not any moon of Saturn. Callisto. The study concluded that a crewed mission to Callisto could potentially be feasible in the 2040s, depending on propulsion technology development. It envisioned a surface base that could serve as an operations center for robotic missions to other parts of the Jovian system, particularly for teleoperated submarines sent down through Europa's ice into its subsurface ocean. It calculated that Callisto's radiation environment would allow surface operations with radiation exposure comparable to what early space station crews experienced, rather than the acute lethal exposure that would apply elsewhere in the Jovian system. The HOPE study did not receive major follow-on funding. It was a planning document, not a mission approval. But its conclusion that Callisto is the uniquely survivable location in the outer solar system for a human presence was based on careful technical analysis rather than speculation. The HOPE study identified what this script has been building toward. Callisto's irrelevance to most space science discussions is not a reflection of Callisto's actual characteristics. It is a reflection of what draws human attention. Drama draws attention. Volcanism, subsurface oceans, the prospect of life, geologically active surfaces, all of these draw attention. Callisto has none of that spectacle. It is old and quiet and cratered. and it is the one place in the outer solar system where the lights could stay on for a human crew. The scale of what surrounds Callisto, when you are standing on its surface and looking up, is something worth picturing. Jupiter would appear roughly 60 times larger in Callisto's sky than the full moon appears in ours. Not 60 times brighter, though it would be extraordinarily bright, but 60 times wider in angular diameter. It would dominate the sky in a way that nothing dominates our own. The gas giant's bands of cloud and the swirling pattern of its atmosphere would be visible to the naked eye. The Great Red Spot, the massive storm that has persisted for centuries on Jupiter, would be visible when it was facing Callisto. The other Galilean moons would be visible as well. Europa, Io and Ganymede would move against the black sky on their own orbital timescales, crossing from one side to the other over hours or days. The entire Jovian system would be arranged like a display around the central planet, visible in all its complexity from Callisto's surface. The Sun, at Jupiter's distance, is roughly 5 times farther away than it is from Earth. Sunlight at Callisto's location is about 25 times weaker than at Earth's surface. The Sun would appear as an extremely bright star, clearly identifiable against the sky, but it would not illuminate the landscape the way our own Sun does from Earth. The surface of Callisto in daylight would be dim by any standard we would recognize, roughly equivalent to a heavily overcast day on Earth. This subdued illumination, combined with the ancient cratered landscape and the immense presence of Jupiter overhead, would create an environment that has no analogue anywhere in human experience. It would be cold, with surface temperatures around negative 140 degrees Celsius. It would be silent, because Callisto's atmosphere is too thin, primarily carbon dioxide and trace oxygen, to carry sound. It would be old, in the sense that the ground beneath your feet would be the most ancient surface you could walk on in the solar system. The thinness of Callisto's atmosphere is worth understanding in context. Callisto does have an atmosphere, but calling it an atmosphere in the way we use that word for Earth, or Venus, or even Mars is slightly generous. It is an exosphere, technically, a collection of molecules loosely associated with the surface that extends upward into space without the pressure and density that we associate with a real atmospheric layer. The primary component of this exosphere is carbon dioxide, with some molecular oxygen detected but not fully confirmed in terms of its abundance. The surface pressure is estimated to be trillionths of an atmosphere at the surface level. It provides no thermal insulation, no protection against micrometeorite impacts, and no meaningful protection against radiation beyond what Callisto's distance from Jupiter already provides. This means that any surface habitation on Callisto would require fully pressurized, sealed structures. There would be no stepping outside without a full pressure suit. The surface environment would require the same kind of life support infrastructure that any deep space habitat requires. In this respect, Callisto is no different from any other airless moon or asteroid. The distinction Callisto offers is not that it is comfortable by any ordinary measure. It is that the specific hazard that makes every other surface in the outer Jovian system so dangerous, the radiation, is reduced to a level where engineering solutions become practical rather than heroic. The cratered surface of Callisto tells a story that extends beyond Callisto itself. In the early solar system, the rate of asteroid and comet impacts was vastly higher than it is today. The planets were still in the process of clearing their orbital neighborhoods. Debris left over from the formation of the solar system remained distributed throughout the system in large quantities. The period of heaviest bombardment, sometimes called the Late Heavy Bombardment, occurred roughly 3.8 to 4.1 billion years ago, when the rate of large impacts was at its highest. On Earth, this early bombardment history has been largely erased. Plate tectonics, weathering, volcanism, and biological processes have continuously recycled Earth's surface. The oldest rocks on Earth date to around 4 billion years ago, and even those have been extensively metamorphosed. The record of the early bombardment is gone from Earth's surface. On the Moon, the bombardment record is better preserved, particularly in the ancient highlands, but lunar volcanism filled many of the largest basins with lava. The record is incomplete. On Callisto, the record is almost intact. Because Callisto has experienced no volcanism and no tectonic activity, its surface has been modified only by incoming impacts, not by any internal process. The crater population on Callisto is a direct record of the impact flux in the outer solar system over billions of years. Every crater size tells you something about the size distribution of the impactors. The density of craters in different regions tells you about the relative ages of those regions. Reading Callisto's surface is reading a history book of the early outer solar system, not a history book that has been edited and revised. The original edition, mostly unmodified, preserved in ice and rock at the edge of Jupiter's gravitational family. Callisto has been visited by spacecraft, but not in the way that Io and Europa have attracted focused attention. Pioneer 10 and Pioneer 11 flew past Jupiter in 1973 and 1974, providing the first close-up images of the Galilean moons. Callisto appeared in those images as a heavily cratered surface, already distinguishable from the active surfaces of the inner moons. Voyager 1 and Voyager 2 flew through the Jovian system in 1979. Their cameras resolved Callisto's craters in more detail and revealed the Valhalla impact basin for the first time. But the Voyager mission schedules prioritized Io and Europa, and Callisto received less observation time. The Galileo spacecraft, which orbited Jupiter for 8 years from 1995 to 2003, made several close flybys of Callisto. These flybys produced the detailed surface maps, composition data, and magnetic field measurements that form the basis of current scientific understanding. The anomalous ionosphere, the possible ocean indications, the surface composition, all of this came from Galileo. But after Galileo, Callisto dropped almost completely off the mission planning map. The two most anticipated upcoming missions, the European Space Agency's JUICE spacecraft and NASA's Europa Clipper, are both fundamentally focused on other targets. Europa Clipper is specifically designed to study Europa. JUICE, despite its name, will spend most of its time studying Ganymede. Both missions will conduct flybys of Callisto along the way, 21 flybys for JUICE between 2031 and 2034, and 9 for Europa Clipper beginning in 2030. But these are gravity assists and opportunistic observations, not the focused study that a dedicated Callisto mission would provide. China's censor has announced plans for a mission called Tianwen-4, targeted for launch around 2029 or 2030, which is planned to enter orbit around Callisto. If this mission proceeds as described, it would be the first spacecraft to orbit Callisto specifically. It would provide a level of sustained observation that no previous mission has achieved. But mission plans change, and Tianwen-4's final configuration remains subject to revision. The scientific return from even one orbiting spacecraft specifically designed for Callisto would be substantial. Questions about the possible ocean, the composition of the surface, the detailed structure of the ancient craters, the nature of the ionosphere, all of these could be addressed at a level of detail that flyby observations cannot achieve. There is a dimension to the Callisto story that goes beyond the scientific and into the practical architecture of how humanity might eventually expand into the outer solar system. The Jovian system is, by any reasonable projection, one of the most resource-rich regions within reach of human technology in the coming centuries. Jupiter itself is a vast reservoir of hydrogen, including both ordinary hydrogen and helium-3, a lighter isotope of helium that is rare on Earth but present in gas giants and would be a potential fuel source for certain proposed fusion reactor designs. The moons of Jupiter collectively contain quantities of water ice, carbon compounds, silicates and metals that dwarf any resource base in the inner solar system. To exploit those resources, to build the kind of presence in the outer solar system that would make humanity a genuinely multi-world civilization rather than a single planet species with a small Mars outpost, you need somewhere to work from. A place where people can live, where machinery can be maintained, where ships can be fueled and resupplied, where long-term scientific operations can be sustained. Every other location in the Jovian system eliminates itself from this role through the radiation environment. You cannot base a sustained human operation at Io. You cannot easily surface operate at Europa. Ganymede requires substantial shielding and planning. Callisto is the location where the engineering required to keep people alive is manageable rather than overwhelming. This is the deeper disturbing quality of Callisto's neglect. Not that it is a scientifically interesting place that we have not fully studied, though that is true, but that it is the enabling location for everything else we might want to do in the outer solar system, and we have spent 4 centuries since Galileo first saw it treating it as the least interesting of the Galilean moons. The question of what life on Callisto would actually require, in practical terms, is worth thinking through. Getting there is the first challenge. Jupiter is roughly 600 to 800 million kilometers from Earth depending on orbital positions, and a one-way trip with current or near-future propulsion technology would take somewhere between 2 and 7 years depending on the trajectory chosen. This is not an insurmountable challenge, but it is a substantial one. Crew members would spend years in transit before arriving, accumulating radiation dose from cosmic rays and solar particle events during the transit, requiring food and water and air and medical care in transit. On arrival, the surface of Callisto would require pressurized habitats, spacesuits for any external activity, power generation, and continuous supply of consumables that could not easily be locally produced from day one. The bootstrapping problem for any outer solar system settlement is severe, but it is less severe on Callisto than anywhere else at Jupiter. The water ice on the surface provides a starting point for oxygen and hydrogen production that other outer solar system locations cannot offer at the surface. The geological stability means the ground is not shifting, not collapsing, not subject to the tidal deformation that cracks Europa's ice. The radiation environment means that surface operations can be conducted with less shielding infrastructure than any other Jovian destination. The NASA HOPE study in 2003 envisioned that early Callisto infrastructure could be operated telematically, with robotic systems building habitat modules, mining ice, and establishing power generation before the first crewed mission arrived. This is the model used for current Mars planning. The same approach could plausibly apply to Callisto, delayed by the greater distance and the greater transit time, but not fundamentally different in its logic. The title of tonight's script calls Callisto the scariest moon we have ignored. It is worth being precise about what is scary here. The surface of Callisto is not threatening in any dramatic way. There are no erupting volcanoes, no tidal forces cracking the ice beneath your feet, no radiation environment that would kill you overnight. Callisto's surface is about as dangerous in the acute sense as a cold, airless, low-gravity rock can be, which is to say it requires serious engineering to survive there. But the specific hazards are not extreme compared to the rest of the Jovian system. What is scary about Callisto is the mirror it holds up. We have spent decades focused on the dramatic moons, the volcanic one, the ocean one, the largest one, and in focusing on them, we have built a mental map of Jupiter's system in which Callisto is a background character. The quiet sibling, the one that does not make the news. But the thing that Callisto does not have, radiation at lethal levels, is the one thing that makes the difference between a place where humans could eventually work and a place where they cannot. And the thing it does have, an ancient, undisturbed surface recording billions of years of solar system history, is something no other world in the solar system can offer. The scariness of Callisto is the kind that creeps up on you. The realization that the most overlooked destination in a system of dramatic and celebrated worlds turns out to be, in the most practical sense, the most important one. That 4 billion years of stillness have made it the most legible geological record in the outer solar system, that its exclusion from Jupiter's radiation belt, an accident of orbital distance, gives it a property no other Jovian moon possesses. We walked past it for 4 centuries. We named it after a nymph from Greek mythology. We gave it a paragraph in the textbook, while its siblings got chapters. We sent spacecraft past it as an afterthought on the way to study its more photogenic neighbours. And it waited, as it has always waited. Patient and ancient and deeply scarred from a solar system that was still young when those craters first formed. Sitting outside the radiation belt, holding its water ice on the surface, offering what no other moon in Jupiter's family can offer. A place where the lights could actually stay on. The discovery of the Galilean moons in January 1610 was one of the pivotal moments in the history of astronomy, not just because of the moons themselves, but because of what they proved. Galileo observed 4 points of light close to Jupiter that moved from night to night in ways that made sense only if they were orbiting the planet. Some nights all 4 were visible. Other nights 1 or more had passed behind Jupiter or in front of it. By tracking their positions over several nights, Galileo deduced that 4 moons were orbiting Jupiter, that their orbital periods were different, and that the inner ones moved faster than the outer ones. This was a direct contradiction of the prevailing cosmological model of the time, the Ptolemaic system, which held that Earth was the centre of all celestial motion and everything in the sky revolved around it. Here were 4 objects that clearly revolved around Jupiter, not Earth. The moons of Jupiter were proof that not everything moved around Earth. The universe was different from how it had been understood. Callisto, as the outermost of the 4 moons, was a key part of this discovery. Its slower, wider orbit compared to Io, Europa and Ganymede helped Galileo establish the pattern. A planet, meaning a wandering object in the terminology of the time, could have its own moons. The solar system was more complex than the Earth-centered picture allowed. The intellectual reverberations of this discovery took decades to fully propagate through natural philosophy. Galileo himself was famously placed under house arrest, in part because of the implications of his telescopic observations. But the moons of Jupiter were not secret. Other astronomers could see them. Simon Marius, independently, saw the same objects and gave them their names. The evidence was replicable, as good evidence always is. 4 centuries later, the 4 moons discovered in January 1610 have become among the most scientifically significant objects in the solar system. Io has been recognized as the most volcanically active world we know. Europa has been identified as one of the most promising candidates for extraterrestrial life. Ganymede has revealed itself to be a world with its own magnetic field and subsurface ocean. And Callisto, the fourth one, sits outside the radiation belt and holds the oldest surface in the solar system and waits to be properly studied. One of the less discussed aspects of Callisto's potential for human habitation is what the view from its surface would teach. Jupiter at Callisto's distance appears about 60 times larger in angular diameter than the full moon appears from Earth. But Callisto is tidally locked to Jupiter, meaning it always presents the same face toward the planet. On the Jupiter-facing hemisphere of Callisto, Jupiter would be permanently visible in the sky, never rising or setting, simply hanging there at a fixed position overhead, cycling through its phases as the sunlight illuminates different fractions of the planet's face over the course of Callisto's roughly 17-day orbit. From the hemisphere of Callisto that faces away from Jupiter, the planet would never be visible. The sky would be dominated by stars and, when the geometry was favourable, by the distant sun. The practical implications of this tidal locking are significant for any settlement design. A base on the Jupiter-facing hemisphere would have a continuous view of the planet and would benefit from some Jupiter shine, reflected light from Jupiter illuminating the surface, particularly at night. The other three Galilean moons would be visible as bright points of light moving across the sky, their positions changing hour by hour and day by day in predictable patterns. A base on the anti-Jupiter hemisphere would never see the planet, but would have a cleaner view of the sky for optical astronomy. The thermal environment might also differ slightly between hemispheres due to the contribution of Jupiter's infrared radiation to the surface energy budget on the near side. Scientific research conducted from Callisto's surface rather than from orbit would have advantages for certain kinds of work. Low-frequency radio astronomy, which is difficult from Earth and from Earth orbit due to interference from terrestrial radio sources and the ionosphere, might be conducted from Callisto's anti-Jupiter hemisphere. The radio environment there would be among the quietest in the inner solar system. Observations of Jupiter itself at radio frequencies, which produces significant natural radio emissions, could be conducted from the Jupiter-facing hemisphere with a level of proximity and consistency that no Earth-based observatory can match. The internal structure of Callisto, and how it compares to the other Galilean moons, tells a story about the conditions in the early Jovian system that is not fully appreciated. All four Galilean moons formed from the disk of gas and dust that surrounded Jupiter in the early solar system. They accreted from similar material, rocky silicates, water ice, carbon and nitrogen compounds, and metal phases that settled from the nebula. But they formed under different conditions at different distances from the young hot Jupiter. Io, the innermost moon, formed in a warmer environment where water ice was less stable. Its composition reflects this. It is the densest of the four Galilean moons, containing a larger proportion of rocky and metallic material relative to ice. Io has been so thoroughly processed by tidal heating that its surface and interior have been completely transformed from whatever they were at formation. Europa is intermediate, rocky but with a significant water fraction, believed to have a water layer amounting to perhaps 10 to 15% of its mass. Whether this water layer is predominantly the buried liquid ocean that spectroscopy and gravity measurements suggest, or whether it is primarily ice with a thinner liquid layer, is one of the questions Europa Clipper is designed to answer. Ganymede is larger still, with a composition that includes more ice than Europa relative to rock. Its internal differentiation, driven by tidal heating and possibly by radioactive decay, produced a rocky core, a water ice mantle, and an icy outer shell with possible liquid layers between them. Callisto, the outermost and coldest, is believed to have never fully differentiated. Its roughly equal mix of rock and ice, distributed throughout the interior without the clear layering of the inner moons, reflects a formation and cooling history in which heat never built up sufficiently to drive the heavier rocky material to the center and the lighter ice to the surface. The rock and ice are mixed together throughout, in a structure that planetary scientists call partially differentiated or undifferentiated. This undifferentiated interior is itself scientifically important. It preserves information about the conditions during formation that the other moons have overwritten through their own geological evolution. The mixing ratio of rock to ice, the identity and abundance of different mineral phases in the rocky component, and the specific composition of the volatile ices all speak to what was present in the Jupiter-forming disk when Callisto accreted. Studying Callisto's interior composition in detail, which requires geophysical measurements from an orbiting spacecraft over a sustained period, would constrain models of how the Jovian system formed in ways that are not accessible through the other moons. The distance that defines Callisto's character, its position at the outer edge of the Galilean system, also shapes what a view of the Jovian system from Callisto would reveal about the system itself. From Earth, the Galilean moons are all visible as a line of points flanking Jupiter, their positions changing over hours and days as they orbit. Telescopic observers since Galileo have been able to watch the moons move, track their orbital periods, and observe the shadow transits when a moon passes in front of Jupiter and its shadow falls on the planet. From Callisto, this familiar picture would be transformed. Jupiter would be vast and close, filling a significant portion of the sky on the near side. Io, at roughly 1/3 of Callisto's distance from Jupiter, would be visible as a distinct disk, not merely a point of light. Its volcanoes, some of which erupt to heights of hundreds of kilometers, would be within range of modest telescopes operated from Callisto's surface. Europa and Ganymede would also be visible as disks. Their surface features resolvable with instruments that would be considered modest by modern standards. The orbital dynamics of the four moons, the Laplace resonance that locks Io, Europa and Ganymede into their coupled orbital periods, would play out visibly in the sky above a Callisto base. The conjunctions, the alignments when two or more moons appear close together in the sky, would occur with predictable regularity. Eclipses, when one moon passes into Jupiter's shadow, would be observable from the surface. The Jovian system, from Callisto, would be a dynamic, observable system of worlds in motion, not the distant collection of points that Earth-based observers see. A scientific culture based on Callisto would have a fundamentally different relationship to the Jovian system than any Earth-based astronomy has ever provided. The comparison between Callisto and Mars as a potential human destination is not often made, but it is instructive. Mars has become the default answer to the question of where humanity should go next. It has a day length close to Earth's, polar ice caps, a thin atmosphere, a complex geological history, evidence of ancient rivers, and a surface radiation environment roughly 250 times higher than Earth's average, but still manageable with shielding. Mars is closer to Earth than the Jovian system by a large margin, with transit times of roughly 6 to 9 months versus years for Jupiter. Callisto's advantages over Mars are more specific. The radiation environment on Callisto's surface is actually lower than on Mars in terms of daily dose. Mars has no global magnetic field and a thin atmosphere that provides minimal protection from galactic cosmic rays and solar particle events. Callisto is outside Jupiter's main radiation belt, and while it also lacks an atmosphere providing meaningful shielding, its orbital position naturally attenuates the most intense radiation. Callisto's surface gravity is about 1/3 of Mars's, which is both an advantage and a disadvantage. An advantage in terms of launch energy required to depart the surface and continue into the Jovian system. A disadvantage in terms of long-term human health effects of low gravity. The water ice on Callisto's surface is directly accessible in a way that Mars's water ice, locked in polar caps or permafrost, is somewhat less straightforward to extract and process. The sheer quantity of water ice on Callisto, constituting a large fraction of the Moon's total mass, exceeds what is available in Mars's accessible polar deposits by a wide margin. The distance from Earth is Callisto's primary disadvantage relative to Mars. A round trip to Callisto and back would require many years even under optimistic propulsion assumptions. Communication delays at Jupiter's distance range from roughly 33 to 53 minutes one way, depending on orbital geometry. Real-time communication with Earth would be impossible. Crew members would need to be genuinely autonomous, making decisions on their own without waiting for guidance from Earth. But the outer solar system is where the resource base for a truly spacefaring civilization lies. The inner solar system, including Mars, represents a relatively limited resource environment. The outer solar system, with its vastly greater quantities of water, carbon compounds, nitrogen, and potentially helium-3, represents the long-term resource future for any civilization that intends to operate at scale in space. A Callisto base, situated between the resource-poor inner solar system and the resource-rich outer solar system, could serve as the pivot point for that transition. There is a class of question in planetary science called the comparative planetology question, and it is one of the most powerful tools available for understanding any individual world. Comparative planetology asks, what can you learn about one world by comparing it to another with similar or different properties? By studying how two objects differ, you can often isolate the effect of a specific variable. Mars and Earth have similar masses and similar distances from the Sun, but Mars has no active plate tectonics and no global magnetic field. Comparing the two reveals how these missing processes affect planetary evolution. Venus and Earth are close to the same size, but Venus is far hotter and lacks liquid surface water. Comparing them illuminates how initial conditions and atmosphere composition can produce radically different outcomes from similar starting material. The 4 Galilean moons of Jupiter are a natural set for comparative planetology. They formed from similar material in similar conditions, but at different distances from Jupiter, producing very different objects. Io, Europa, Ganymede, and Callisto represent a gradient of orbital distance from Jupiter, a gradient of composition, a gradient of tidal heating, and a gradient of geological activity. By studying all 4 systematically, you can isolate the effects of tidal heating from other variables. You can understand how the same initial material evolves differently under different heat inputs. You can trace how differentiation progresses as more heat is available. You can see the full range from the geologically dead, undifferentiated Callisto to the volcanically hyperactive, fully differentiated Io. This systematic comparison requires data of comparable quality from all 4 moons. Right now, we do not have that. Io has been studied closely by multiple spacecraft. Europa has been a priority for missions since Galileo revealed its cracked surface. Ganymede will receive intensive study from JUICE. And Callisto has received considerably less dedicated attention. The comparative planetology case for studying Callisto is not primarily about what is interesting about Callisto specifically. It is about what Callisto can reveal in comparison to the other three. Callisto is the control case, the end of the gradient, the world with the least heat input and the least geological processing. Without Callisto fully characterized, the gradient is incomplete. The scariness of Callisto is worth coming back to one more time before we close, because it is a specific kind of scariness that deserves precise description. It is not scary because it is dangerous in any dramatic way. Callisto will not erupt, will not crack open, will not irradiate you to death in hours. It is cold and airless and ancient, but those are characteristics shared by many objects in the solar system and are manageable with appropriate technology. The scariness is conceptual. It is the scariness of realizing that the thing you overlooked was the thing that mattered most, that the quiet sibling turned out to be the practical one, that the moon with the most ancient surface and the least dramatic activity is the only one in its neighborhood where the lights could stay on for human beings. It is also the scariness of implication. If Callisto is the most important destination in the Jovian system for human operations, and we have been systematically underinvesting in understanding it for 4 centuries since its discovery, what else are we systematically misreading in the solar system? What other apparently boring, apparently dead, apparently overlooked objects are quietly waiting to turn out to be more consequential than the dramatic ones that captured our attention? Science is a discipline of looking at what is actually there, rather than what you expect, or what is most visually arresting. But science operates within human psychology, and human psychology responds to drama. The volcano, the hidden ocean, the magnetic field, all of these are dramatic in ways that an ancient cratered surface is not. Callisto is a test case for whether we can maintain scientific interest in the undramatic, in the thing that is important precisely because it lacks the features that typically generate excitement. In the world that, in a family of dramatic siblings, chose to be the patient one, the stable one, the one that sat outside the chaos and accumulated the record. It turns out that outside the chaos, in the cold and the dark, with its ancient craters and its frozen water and its position just beyond the belt of charged particles that would kill everything else, Callisto has been doing exactly what the most important things often do. Still waiting. The future that Callisto represents, if it is ever taken seriously as a human destination, is worth describing in slightly more concrete terms than abstract potential. Imagine a research station on Callisto's near side, in the shadow of a modest crater rim that provides some protection from micrometeorite impacts and attenuates the already manageable radiation dose a little further. The habitat modules are pressurized and warm against the cold that falls to negative 140 degrees Celsius outside. Through a heavily insulated window, Jupiter fills a significant fraction of the sky. The banding of Jupiter's atmosphere is visible. The great red spot, when it faces Callisto, is clearly distinguishable as a dark oval in the southern hemisphere. The crew has 3 primary tasks. They operate a network of robotic systems across the Jovian system. A set of small rovers is crawling across Europa's surface ice, drilling down to take samples. A submarine, deployed through a previously drilled hole, is operating 3 kilometers below the ice in Europa's ocean, guided in near real time by crew members whose instructions travel the distance between the 2 moons in about 30 seconds. A flying probe is sampling the atmosphere above Io, collecting data on the composition of the volcanic plumes. None of this could be done from Earth. The communication delay to Earth from this location is 43 minutes one way today in the current orbital configuration. By the time Earth learned something unexpected had happened to the submarine and sent an instruction, 90 minutes would have passed. In 30 seconds, a Callisto-based controller can respond, redirect, adapt. The crew also conducts their own science on Callisto itself. The geologist in the group has been mapping a section of Callisto's surface in high resolution, cataloguing craters, measuring the dark material composition, looking for signs of the slow surface processes that planetary scientists have inferred from orbital data, but never observed directly. The materials scientist is experimenting with local ice and rock samples, testing their suitability for habitat construction and manufacturing. They are doing science in the outer solar system in a way that is not possible from Earth and not survivable at the inner moons. They are there because Callisto, the quiet one, the overlooked one, the ancient one, sits outside the belt of charged particles that would have made all of this impossible everywhere else. There is something that stands just outside the edge of all the practical considerations. Callisto's surface has not changed in any meaningful way for most of the age of the solar system. The craters you would see if you stood on its surface were there before the first fish appeared on Earth. The Valhalla Basin was already ancient when multicellular life was first beginning to experiment with complexity on our planet. The ridges and troughs of those ancient impact rings have been sitting in the cold and the dark for longer than anything alive today has any connection to. To stand on Callisto's surface would be to stand on the oldest outdoor landscape that any human would ever stand on. Not old in the way that Earth's oldest rocks are old. Old in the sense of unmodified, unchanged, exactly as it was when the solar system was young. The texture of the ground beneath you would be the texture of the early solar system. That is not exactly comforting. But it is not supposed to be. The outer solar system is not comforting. It is vast and cold and ancient and indifferent, and Callisto, the most ancient surface in the solar system, is the most concentrated expression of all of those things. To understand Callisto properly, you need to understand what the orbital resonance it is excluded from actually does to the moons that are inside it. The Laplace resonance, the specific gravitational relationship linking Io, Europa, and Ganymede, is one of the most consequential physical arrangements in the solar system. It works because the three moons are locked into a ratio of orbital periods. For every one orbit Ganymede completes around Jupiter, Europa completes exactly 2, and Io completes exactly 4. This ratio is not approximately maintained. It is exact, to within the precision of any measurement we can make. The consequence of this locked ratio is that every few orbits, all three moons align on the same side of Jupiter simultaneously, and their mutual gravitational tugs reinforce rather than cancel out. The alignment creates periodic forcing of each moon's orbit, preventing the orbits from becoming perfectly circular. Instead, each moon's orbit has a small but maintained eccentricity, meaning it moves slightly closer to and slightly farther from Jupiter over the course of each orbit. For Jupiter's gravity, this varying distance matters enormously. The difference in gravitational pull between a moon's closest and farthest approach in each orbit is enough to deform the moon's body. Jupiter's gravity literally squeezes the moon slightly at closest approach and releases it at farthest approach, over and over, once per orbit. For Io, which orbits every 1.77 Earth days and whose orbit has the highest eccentricity in the resonance, this flexing is continuous and powerful. Geologists can estimate the heat production from tidal dissipation in Io's interior and compare it to the observed volcanic activity. The match is extraordinary. The heat coming out of Io matches the calculated tidal heating input within measurement uncertainty. Io's hundreds of volcanoes are directly powered by Jupiter's gravity, mediated through the orbital resonance that Callisto does not participate in. For Europa, the tidal heating is less extreme than for Io, but it is enough to maintain the temperature of the buried ocean above freezing across the entire moon. Without the resonance, without the orbital eccentricity, without the tidal heating, Europa's ocean would freeze from the bottom up over geological time. The resonance is what keeps it liquid. The resonance is what makes Europa so scientifically compelling. Callisto, at its greater distance, is not locked into this resonance. Its orbit has very low eccentricity. Jupiter's tidal flexing of Callisto's interior is minimal. There is effectively no tidal heating, and so Callisto's interior remains cold and its surface remains ancient, and its craters remain undisturbed. The resonance that makes Io volcanic and Europa oceanic is also the thing that makes Callisto geologically dead. The moons inside the resonance are active because of it. The moon outside it is preserved because of its absence. The surface composition of Callisto provides important constraints on its history, and the composition is more varied and interesting than the word cratered suggests. Spectroscopic observations from both ground-based telescopes and the Galileo spacecraft have identified several distinct materials on Callisto's surface. Water ice is the dominant component in many regions, but it is mixed with dark material whose exact composition remains debated. This dark material appears in crater floors, in the material ejected by impacts, and in the general background composition of the regolith. The dark material on Callisto is not fully characterized. It may include carbonaceous compounds, organic molecules, and various mineral phases that have been altered by billions of years of cosmic radiation and micrometeorite bombardment. Some of the spectral features match those of carbonaceous chondrite meteorites, a class of primitive meteorites that are thought to represent some of the most chemically unaltered material in the solar system. If this interpretation is correct, the dark material on Callisto's surface may contain some of the most pristine chemical inventory from the early solar system. Not just geological history in the form of craters, but chemical history in the form of organic and mineral compounds that have been sitting on Callisto's surface almost unmodified since the solar system was young. Silicate minerals have also been detected. Magnesium and iron-bearing hydrated silicates appear in Callisto's spectra, suggesting that water and rock have interacted chemically at some point in the moon's history, either during formation or during early warm periods when liquid water may have been present before the interior cooled. Carbon dioxide ice has been detected in spectroscopic observations. So have sulfur-bearing compounds and possibly nitrogen compounds. The chemical inventory on Callisto's surface is not as simple as water, ice and rock. It is a complex mixture of materials that tell a story about the conditions in the outer solar system during and after planetary formation. For any future human presence on Callisto, this chemical diversity has practical implications. Carbon compounds can be chemical feedstocks. Nitrogen, if present in accessible forms, could contribute to atmosphere construction. Sulfur compounds have industrial uses. The surface is not just a flat, icy plain. It is a chemical laboratory frozen in time, waiting to be sampled. The gravity on Callisto is a significant practical consideration that most discussions of outer solar system settlement skip over quickly. Callisto's surface gravity is approximately 0.126 times Earth's surface gravity. For comparison, the Moon's surface gravity is about 0.165 times Earth's, and Mars has about 0.376 times Earth's gravity. Callisto's gravity is lower than the Moon's, which is itself already low enough to pose significant health challenges for long-duration human presence. Extended time in very low gravity produces a well-documented set of physiological effects. Bones lose density because the skeletal system no longer needs to support the same mechanical loads it was designed for. Muscle mass decreases, particularly in the legs and lower back. The cardiovascular system adapts to the reduced demand placed on it by low gravity and becomes less efficient at pumping blood against gravity when the person returns to higher gravity environments. Fluid distribution in the body shifts, producing changes in intracranial pressure that may affect vision over long timescales. The threshold below which these effects become irreversible or unacceptably severe is not well established. We have extensive data on human physiology and microgravity from the International Space Station. We have almost no direct data on long-duration human presence at low but non-zero gravity levels like those of the Moon, Mars or Callisto. Callisto's gravity is low enough that any long-duration human settlement would need either to accept the health consequences of prolonged low-gravity exposure or to design rotating habitats that use centripetal acceleration to simulate higher gravity during sleep or exercise periods, or to develop medical interventions that counteract the physiological effects of low gravity. This is a challenge. It is a real one. But it is the same challenge that would apply to any moon of Jupiter, since all 4 Galilean moons have similar low gravities. It is not specific to Callisto. What is specific to Callisto is that it is the only Galilean moon where this challenge would not be compounded by the immediate and lethal radiation environment that makes the inner moons so dangerous. The history of Callisto's naming and its relative obscurity in popular culture reflects something about how we rank worlds in our imagination. Callisto was discovered simultaneously and independently by Galileo Galilei and by Simon Marius in January 1610. The convention that prevailed for most of the following centuries named the moons by their order from Jupiter, with Callisto being designated Jupiter the fourth and outermost of the Galilean satellites. The names Io, Europa, Ganymede and Callisto came from Simon Marius, who drew them from figures in Greek and Roman mythology associated with Jupiter and Zeus. Callisto was a nymph who became a hunting companion of the goddess Artemis in some versions of the myth, and was later transformed into the constellation Ursa Major, the Great Bear, in an origin story that varies across different ancient sources. These mythological names were not widely adopted until the 20th century. For most of the astronomical tradition, the moons were simply numbered. Callisto was the 4th one. The shift in cultural perception that followed the Voyager missions in 1979 elevated Io and Europa dramatically. Io's volcanic surface, revealed for the first time in Voyager's images, was genuinely unlike anything previously seen in the solar system. Europa's cracked, smooth surface looked like a frozen ocean, and within years researchers were calculating what a buried liquid ocean might mean for the possibility of life. These discoveries gave Io and Europa identities in the popular imagination that Callisto never acquired. Callisto looked, from Voyager's images, like a moon that had been hit a lot. A heavily cratered surface with no immediately dramatic features does not generate the same cultural response as volcanoes or possible subsurface oceans. The public memory of Callisto became defined by what it lacked compared to its siblings, rather than by what it had. This cultural underweighting has had practical consequences. Mission planning responds partly to public interest and scientific excitement. The missions that generate the most enthusiasm get funded. The missions to Europa and Io reflect that enthusiasm. Callisto's more subdued identity is translated, perhaps unfairly, into fewer dedicated mission resources. There is a comparison worth making between Callisto and another world that long suffered from a similar reputation for being the boring one, For most of the 20th century, Pluto was considered a minor curiosity, the smallest and coldest and most distant of the planets, later demoted to dwarf planet status, generally treated as a rocky lump of frozen methane with nothing particularly interesting going on. Planetary scientists knew it existed. They knew it was there, but before the New Horizons mission arrived in 2015, relatively few resources had been directed toward understanding Pluto specifically. When New Horizons flew past Pluto, it revealed a world with mountain ranges made of water ice rising to heights comparable to Earth's Rocky Mountains. It revealed a vast plain of nitrogen ice, showing evidence of active convection, with material cycling through the surface continuously. It revealed haze layers in the atmosphere, complex chemistry, a layered interior, and geology so varied and so active that the scientific community was genuinely caught off guard. The quiet, boring, cratered world that nobody prioritized turned out to have been actively interesting the whole time. The scientific payoff from New Horizons exceeded expectations substantially. Callisto's situation has a different quality from Pluto's. Callisto is genuinely old and geologically quiet in ways that Pluto turned out not to be. The cratered surface is a real feature of the Moon's real history, not a mischaracterization, but the lesson of Pluto is relevant nonetheless. The worlds we dismiss as boring often contain things we did not anticipate, and the cost of not looking closely is not knowing what we missed. Callisto almost certainly has surprises waiting. The possible ocean is one. The detailed composition of the dark material on the surface is another. The structure of Valhalla and the other large impact basins, examined closely by an orbiting spacecraft, would tell a story about the impactor population in the early outer solar system that we cannot currently read in full detail. The ionosphere and its implications for the internal structure of the Moon are not yet resolved. Callisto's surprises may not be as visually dramatic as Pluto's, but in the context of what the outer solar system means for the long-term future of human civilization, Callisto's practical attributes may turn out to be more important than any single dramatic geological feature. The scale of Jupiter's magnetosphere is something worth understanding as a physical environment, because it is the defining feature of the Jovian system for any biological or technological presence. Jupiter's magnetic field is produced by the circulation of metallic hydrogen in the planet's deep interior, where the pressure is high enough that hydrogen transitions to a metallic state and conducts electricity. The resulting dynamo generates a magnetic field roughly 20,000 times stronger than Earth's. This powerful field extends into space and creates the Jovian magnetosphere, one of the largest structures in the solar system. If Jupiter's magnetosphere were visible to the naked eye from Earth, it would appear several times larger in the sky than the full Moon, despite being 5 times farther away. It is a vast, dynamic, invisible presence dominating the space around Jupiter. Within this magnetosphere, charged particles, primarily protons and electrons, are accelerated to high energies and trapped in radiation belts that have a roughly toroidal shape, like an enormous donut of invisible radiation surrounding the planet. The inner radiation belt, the most intense region, extends out to roughly 3 to 4 Jupiter radii from the planet's center. Io orbits at about 5.9 Jupiter radii. It sits well within the radiation belt. The particles that have been accelerated by the magnetic field slam into Io continuously, stripping material from its surface in a process called sputtering and contributing to the torus of sulfur and oxygen ions that surrounds Io in its orbit. Europa orbits at about 9.4 Jupiter radii. Still within the radiation belt, receiving a lower but still lethal dose compared to Io. Ganymede orbits at about 15 Jupiter radii. It has its own small magnetosphere which creates some local shielding, but it still sits within Jupiter's main radiation environment. Callisto orbits at approximately 26.3 Jupiter radii. This places it just outside the main radiation belt. The charged particles that make the inner moon so dangerous are substantially attenuated at Callisto's distance. The magnetosphere still reaches Callisto, the ionosphere observations confirm that much, but the flux of high-energy particles at the surface is vastly lower than at any of the inner moons. The specific number that emerges from this geometry, 0,001 rems per day, is not an accident of good fortune. It is a direct consequence of orbital distance and the physical structure of Jupiter's magnetosphere. Callisto's habitability relative to the other Galilean moons is not a quirk or a marginal effect. It is a large and physically systematic difference. The future of human spaceflight, on any timescale beyond the near term, involves confronting the question of where in the solar system humanity wants to go and what it wants to do when it gets there. Mars is the immediate next step in most planning documents. The moon is being revisited as a stepping stone. Beyond that, various proposals exist for crewed missions to asteroids, to the moons of Mars, to Venus flyby missions. The general trajectory of ambition extends outward, but the outer solar system represents a different scale of ambition. Not a few years of travel, but perhaps a decade of transit time with foreseeable technology. Not radiation environments slightly elevated above Earth's, but environments that would kill unprotected humans within hours. Not modest geological challenges, but extreme cold, extreme remoteness, and resource profiles that look very different from the inner solar system. In this context, the property that Callisto uniquely possesses, a radiation environment that falls within manageable engineering parameters, is not merely interesting. It is enabling. Without Callisto, planning for a sustained human presence in the Jovian system becomes a problem of extraordinary difficulty. With Callisto, it becomes a problem of ordinary difficulty, long transit times, resource extraction, habitat construction, medical considerations for low gravity, all of which are challenging, but are challenges we already know how to think about. Every major Jovian moon mission in history has been conducted by robotic spacecraft. This is the only viable approach for Io, Europa and Ganymede given their radiation environments. Sending humans to those surfaces would require infrastructure investments for radiation shielding that would make the missions exponentially more complex and expensive. Callisto changes the calculation. A human crew on Callisto could operate with radiation exposure comparable to extended missions on the International Space Station, not safe in any absolute sense. But not a mission-ending hazard. The difference between a crewed station in low Earth orbit, where astronauts have lived for months at a time, and a crewed station on Callisto's surface is primarily one of distance, not radiation physics. The oxygen enigma that planetary scientists mention in connection with Callisto is worth understanding because it hints at processes that are not yet fully explained. Callisto's ionosphere was detected by the Galileo spacecraft through radio occultation measurements. When Galileo's radio signal passed through Callisto's ionosphere before reaching Earth, the signal was bent and delayed in ways that allowed scientists to calculate the electron density in the ionosphere. The values they found were higher than could be explained by the amount of carbon dioxide known to be in Callisto's thin atmosphere. Carbon dioxide can be ionized by sunlight to produce electrons, but not enough electrons to account for what was observed. The additional ionization requires additional material being ionized. The leading candidate is molecular oxygen. If Callisto's atmosphere contains molecular oxygen at concentrations 10 to 100 times higher than the carbon dioxide content, the electron density in the ionosphere would match the observations. The question of where this oxygen comes from is the enigma. Molecular oxygen at Callisto's temperature would quickly freeze out onto the surface and be lost from the atmosphere. Something must be continuously producing it. The most straightforward source is radiolysis, the decomposition of water ice molecules by radiation. High-energy particles from Jupiter's magnetosphere strike water ice on Callisto's surface, breaking the water molecules into hydrogen and oxygen. The lighter hydrogen escapes to space while the heavier oxygen remains. But current estimates of Callisto's radiation environment, which is low compared to the inner moons, suggest that radiolysis alone may not produce oxygen fast enough to maintain the observed atmospheric levels. There is a discrepancy between production and observation. One proposed resolution is that Callisto has a reservoir of molecular oxygen trapped within the porous surface ice, accumulated over billions of years, that slowly releases into the atmosphere as it is heated. If this is correct, the oxygen in the atmosphere is not being produced continuously by radiation, but is instead being released from a vast subsurface store that accumulated over geological time. This possibility has implications. It means Callisto's subsurface may contain substantial quantities of oxygen, which is a resource of extraordinary value for any life support system. Oxygen trapped in the surface ice, releasable with modest heating, would dramatically simplify the life support calculations for any human settlement. The oxygen enigma is not resolved, but its possible solutions all point toward a more resource-rich environment than Callisto's surface appearance suggests. The quietest moon in Jupiter's family turns out to be the one keeping the most complete record. The one we ignored turns out to be the one we should have been studying all along. The one that looks dead turns out to be the only one where something could live without dying first. The ancient nature of Callisto's surface creates a counterintuitive relationship with science that is worth spelling out. In most areas of planetary science, a geologically active world is considered more scientifically valuable than a geologically dead one. Volcanically active worlds tell us about current processes. Tectonically active worlds tell us about how planets change in real time. Worlds with liquid water oceans tell us about the conditions where life might arise. All of this activity makes for dramatic science with urgent questions. Callisto inverts this. Its geological death is the source of its unique scientific value. Every crater on its surface is a data point in a dataset that no other world in the solar system can provide at the same resolution or completeness. The crater record on Callisto is to the history of the outer solar system what tree rings are to the history of a forest, a continuous, datable record of what happened over time. By measuring the size distribution of craters across Callisto's surface, scientists can reconstruct the size distribution of the objects that struck it. By comparing regions of different crater density, scientists can establish relative age relationships. Fewer craters means younger surface, more craters means older surface. By comparing the crater population on Callisto to those on the other Galilean moons, scientists can identify which periods of bombardment affected the whole Jovian system and which events were more localized. The late heavy bombardment, that period roughly 3.8 to 4.1 billion years ago, when impact rates were significantly elevated, is recorded in the crater populations of the Moon, Mars, Mercury, and the outer planets' moons. Callisto's record of this period is the most complete and least disturbed. The details of exactly when the bombardment began, how long it lasted, and how the impact rate declined afterward are encoded in Callisto's cratered surface in ways that geologically active worlds have overwritten. Resolving these questions would improve our understanding of the early solar system for every object in it, including Earth. The history of large impacts on Earth, which may have played a role in the delivery of water and organic molecules that eventually became life's raw materials, is connected to the same population of impactors that cratered Callisto. Callisto is not just a record of what happened at Jupiter. It is a record of what was happening throughout the solar system during its most dynamic early period. The 3 incoming missions to the Jovian system that will conduct Callisto observations deserve individual attention because they represent different approaches and different questions. The European Space Agency's Jupiter Icy Moons Explorer, universally abbreviated as JUICE, launched in April 2023 and is currently en route to Jupiter, scheduled to arrive in 2031. JUICE's primary scientific objective is Ganymede, where it will eventually enter orbit, making it the first spacecraft to orbit a moon of another planet other than Earth's moon. But before reaching Ganymede, JUICE will conduct 21 close flybys of Callisto between 2031 and 2034. These 21 flybys are not an afterthought. The JUICE mission design specifically uses Callisto for gravity assists to adjust its trajectory toward Ganymede. But during each flyby, JUICE will turn its instruments toward Callisto's surface and atmosphere. The spacecraft carries a radar sounder capable of penetrating the icy crust and mapping what lies beneath, which could potentially reveal the depth and extent of any subsurface liquid water layer. It carries spectrometers for surface composition, a magnetometer for magnetic field measurements, and a camera system for high-resolution surface imaging. 21 systematic encounters with a dedicated science suite will produce more data about Callisto than all previous missions combined. The spatial coverage across Callisto's surface will be extensive. Regions that have never been imaged at high resolution will be covered. The oxygen enigma in the ionosphere may be addressed with better atmospheric measurements. The magnetic field data from 21 passes will constrain the internal structure more tightly than Galileo's limited flybys could. NASA's Europa Clipper, launched in October 2024, is primarily a Europa mission. It will make approximately 50 flybys of Europa to characterize its ocean and the thickness of the ice above it, among other goals. But it will also make 9 close flybys of Callisto beginning around 2030, again primarily for trajectory purposes, but with science instruments active during the encounters. The combination of Europa Clipper and JUICE data from Callisto, collected over roughly the same time period in the early 2030s, will allow comparison of results from 2 independent spacecraft with different instrument suites. Where the 2 missions agree on their measurements of Callisto, that agreement will provide high confidence in the results. Where they disagree, the discrepancies will point toward questions requiring further investigation. There is something worth saying about why a dedicated Callisto orbiter, rather than flyby observations, would represent a qualitative improvement in our understanding. A spacecraft in orbit around Callisto would observe the same surface repeatedly as Callisto rotates beneath it. It would build up coverage over months and years. It would catch seasonal changes, if any exist. It would be able to revisit specific features with different illumination angles to understand their 3-dimensional structure. It would track how the ionosphere changes over time and whether the electron density varies with solar activity or with Callisto's position in Jupiter's magnetosphere. Flyby observations, however numerous, are snapshots. Each pass through the system lasts hours and provides a strip of coverage across the surface. The remaining surface is seen only from large distances with lower resolution. The temporal coverage of any single flyby is constrained by the brief window when the spacecraft is close enough for detailed observation. An orbiter changes this fundamentally. It turns a snapshot into a continuous observation program. Processes that change on timescales longer than a flyby can be captured. Surface features that look different under different illumination conditions can be studied systematically. The subsurface radar can build up a global map of the ice structure rather than sampling a few strips. The science case for a dedicated Callisto orbiter has been made in various planning documents over the years. China's Tianwen-4, if it orbits Callisto as currently described, would be the first mission to provide this sustained observational perspective. The scientific return would be disproportionately large compared to the additional cost over a flyby mission. The analogy between Callisto and a geological archive is useful but limited, and the limitation is worth acknowledging. A geological archive on Earth is a record that humans discovered after the fact, billions of years after the events it records. We find the rock, we analyze it, we extract what information we can from it. The archive exists independently of our interest in it. Callisto is a geological archive of the same kind. We did not create it, we did not design it. We happened to find it, and it turned out to contain a record we had not specifically gone looking for. The fact that Callisto's surface records ancient impact history is not because nature planned for our eventual curiosity. It is because Callisto's specific combination of orbital position, mass, composition and history happened to produce a surface that is both old enough and well preserved enough to serve as a record. What the analogy omits is that Callisto's record is also incomplete. Callisto has its own biases. It is located in the outer solar system, so its crater record reflects the impactor population in that region rather than the inner solar system. Objects that struck Earth and Mars but were too small to cross the asteroid belt and reach Jupiter are underrepresented in Callisto's record. Objects that primarily populated the outer solar system in the early period are well represented. The comparison between Callisto's crater record and the records on the inner planet's moons allows scientists to partially distinguish between these two populations, but the interpretation requires careful modelling. The Callisto record is not a simple direct window into solar system history. It is evidence that must be interpreted using theoretical models of how the impactor population evolved and distributed through the solar system over time. That interpretive work is complex, and it has not been done as thoroughly as the richness of Callisto's record would warrant, in part because the high-resolution data needed to conduct the analysis in full detail has not been collected. A dedicated orbiter, providing global high-resolution coverage, would enable the kind of comprehensive crater analysis that could substantially revise our understanding of early solar system bombardment. There is a specific number that appears in discussions of Callisto that tends to be stated and then moved past without full appreciation. The radiation dose on Callisto's surface is approximately 0.01 rems per day. On Io, it is approximately 3,600 rems per day. This is a ratio of 360,000. Not a few times different, not 10 times different, 360,000 times different. To make this more legible, if you imagined a hypothetical unshielded person standing on Io's surface and another standing on Callisto's surface, the person on Io would receive in 1 second roughly the equivalent of 4 days of Callisto's total daily dose. The person on Io would die within hours from acute radiation syndrome. The person on Callisto would survive without any immediate symptoms, though over months and years the elevated exposure would accumulate health risks. The difference is not just that Callisto is safer than Io. It is that Io, Europa, and to a lesser extent Ganymede represent qualitatively different categories of hazard from Callisto. You can engineer around an elevated radiation environment by a factor of 10 or 20 or even 100 with reasonable shielding infrastructure. You cannot engineer around a factor of 360,000 without creating a habitat that is more about radiation protection than about the scientific work the people inside are supposed to be doing. This is what makes the radiation comparison between Callisto and its siblings so important for any practical consideration of human spaceflight. It is not a quantitative difference on a continuous scale. It is a categorical distinction between moons where sustained human presence is conceivable with foreseeable technology and moons where it is not. The Galileo spacecraft, which studied Callisto more closely than any mission before or since, revealed another feature of the moon that is easily overlooked. Callisto's surface is not the simple uniform cratered plain it appeared to be in Voyager images. At higher resolution, Callisto's surface shows a complexity that was invisible in the lower resolution Voyager data. The crater floors and crater walls have different compositions from the surrounding terrain. The dark material concentrates in certain regions and is absent or thin in others. Small-scale features include bright spots and streaks that suggest relatively recent impacts, geologically speaking, that have exposed fresher material beneath the dark surface layer. There are also features that look superficially like they might be produced by erosion, by some process that has smoothed out fine-scale topography between larger craters. The candidate process is not water erosion, as there is no surface water. It may be the gradual sublimation of volatile ices over billions of years, where ice evaporates slowly and the residual dark material slumps or migrates to lower positions, producing a subtle smoothing effect that affects small craters and gentle slopes. This process, if it is operating on Callisto's surface, would be extremely slow by any standard but cumulatively significant over billions of years. It would be a form of slow geological activity driven not by internal heat but by the interaction between the surface, sunlight, and the vacuum of space. What this means is that Callisto's surface is not simply a passive record of ancient impacts. It is an active system, just an extremely slow one. The dark material is migrating on geological timescales. The volatile ice is sublimating and probably redepositing in different locations. The surface, ancient as it is not completely static. This subtlety has implications for reading the crater record. If surface processes are modifying the appearance of small craters over time, the record of small impactors is not as clean as it might appear. Larger craters which are not significantly affected by these slow surface processes remain more reliable data points, but the fine detail of the impactor size distribution, which requires counting small craters accurately, is partially obscured by slow surface modification. Understanding these processes requires the kind of sustained, repeated observation over time that a dedicated orbiter could provide. Changes in the surface appearance between observations months or years apart could be detected with sufficient imaging capability, providing direct evidence for surface processes that currently remain largely inferential. The long arc of the relationship between humans and the sky above Jupiter will someday, if civilization continues long enough and far enough, involve people who have actually been to the Jovian system and returned to tell about it. What those people will say about Callisto depends entirely on what was learnt about it in the intervening time, and what that knowledge motivated in terms of planning and investment. If the JUICE and Europa Clipper flyby data, combined with whatever Tianwen 4 provides, produces the kind of comprehensive picture that motivates a dedicated crewed mission proposal, Callisto could become as familiar a name in the human spaceflight vocabulary as the Moon or Mars are today. If Callisto remains a background figure, the afterthought moon that gets mentioned when people discuss the Galilean system but never quite earns the dedicated attention that would transform it from known about to understood, then the missions to the Jovian system will continue to be conducted by robots. The science will advance slowly, and the practical potential of the moon as a human staging point will remain unrealized. The choice is not made in a single decision. It is made incrementally, through mission proposals and funding decisions and the slow accumulation of scientific interest that eventually creates the political and financial support for expensive missions. The science that JUICE and Europa Clipper produce from their Callisto flybys will influence that process. Compelling data could accelerate interest. Mundane data could slow it, but the underlying physics does not change. The radiation environment at Callisto will remain what it is. The water ice will remain on the surface, the ancient craters will remain. The position outside Jupiter's main radiation belt will remain. Whatever Callisto's scientific profile turns out to be, its practical attributes as the most habitable location in the Jovian system are determined by physics and geometry, not by our level of interest in them. The question of what future humans might actually do on Callisto, if they were there, is more concrete than it might seem. A base on Callisto would immediately provide the ability to teleoperate robotic systems throughout the Jovian system with drastically reduced communication delays compared to operation from Earth. The one-way communication time from Earth to Jupiter ranges from about 33 to 53 minutes. A delay of that magnitude makes real-time robotic control nearly impossible. Any robotic operation, whether a rover on Io's volcanic surface or a submarine in Europa's ocean, would have to be programmed to operate autonomously for long periods, because any instruction sent from Earth would arrive too late to respond to a fast-changing situation. From Callisto, the communication time to the other Galilean moons would be a matter of seconds to minutes, depending on orbital geometry. True teleoperation with a human controller responding to what a robot is seeing almost in real time would become possible. This is the argument at the center of the NASA HOPE study, a human crew on Callisto conducting remote operations rather than surface operations themselves, could achieve science results at Europa's ocean floor that would be impossible to achieve by any Earth-directed robotic mission. The scientific return from such an operation could be extraordinary. A submarine exploring Europa's ocean, guided in near real time by a human crew on Callisto, who could respond to unexpected observations and redirect the vehicle as conditions changed, would have far greater scientific capability than a fully autonomous submarine that had to execute a predetermined program without adaptive guidance. In this sense, the HOPE vision was not primarily a vision of Callisto for its own sake. It was a vision of Callisto as an enabling platform for everything else in the Jovian system. Callisto's value was not in what was on Callisto, but in what Callisto's location and radiation environment allowed you to do from there. This is a different kind of scientific and exploratory value from the intrinsic scientific value of studying Callisto's ancient surface. It is operational value. And it is the kind of value that, in the long history of human infrastructure development, has often been as important as the intrinsic value of the destination itself. Stand outside tonight and look for Jupiter. If the sky is clear and you know where to look, you can find it as the brightest steady point of light that does not twinkle the way stars do. And somewhere in the faint light coming from that direction, invisible to the naked eye, but resolvable even with a modest backyard telescope, the 4 Galilean moons are moving in their orbits around their planet. Io is in there, volcanic and bright and lethal, Europa is in there, oceanically exciting and equally lethal, without adequate protection. Ganymede is in there, the largest moon in the solar system, partially shielded and deeply scientific. And Callisto is in there. Outermost, quietest, oldest surface. Most cratered, sitting just outside the belt of charged particles that would kill everything else. Nobody's darling, nobody's priority. The moon that does not make the opening chapter of the Jupiter story, even though it may be the most important chapter in the human story of what comes next in the outer solar system. It has been there since Jupiter's earliest formation period. It has been accumulating its crater record since the early solar system. It has been sitting outside that radiation belt for 4 billion years. And it has been waiting, without impatience, without drama, without volcanic eruptions or cracking ice or subsurface oceans making headlines, for someone to finally look at it properly. The missions are coming. JUICE will fly past it 24 times in the 2030s. Europa Clipper will use it as a gravity assist partner. China's Tianwen-4 may orbit it, providing the first sustained observations from a dedicated spacecraft. The data will start arriving within a decade. Europa Clipper will use it for gravity assists while studying its more celebrated neighbour. China's Tianwen-4 may orbit it. The data will arrive, and when it does, Callisto will tell us things about the early solar system, about the resources available in the outer solar system, and about where humans could actually survive in Jupiter's neighbourhood, that no other moon can tell us quite as clearly. The most ignored moon in the most dramatic planetary system in the solar system was not ignored because it had nothing to say. It was ignored because we were not ready to listen. Good night.